Let's start talking about matrices. Now, a matrix is not only a cool movie, it is something that we use to organize information. Okay, we organize it into rows and columns. Okay, and we enclose it all in square brackets. So we have rows that are horizontal and columns that are vertical. Now, we use these matrices to hold information. Okay, hold information. And, okay, so a matrix can be any size, but we need to know that size, which is the order of the matrix. It tells us how many rows there are and how many columns there are. So this describes a 2x3 matrix, 2 rows and 3 columns. And it's always in that order of row, then column. Okay. And within the matrix, we have individual things, which we call elements. Okay. This is a bit more advanced, but we'll go into, which it describes the location of all the positions in there. Now we have several different types of matrices. Now a row matrix is when you have just one row and many columns. Okay, a row matrix. In some books they call it a row vector, but we really just stick with row matrix. You can see here how there's just one row and 3 columns. So that would be a 1x3, and that makes it a row matrix. We have column matrices. So here we have one column and many rows, which is called a column matrix. So you can see I've got 1, 2, 3 rows and 1 column. So that makes it a 3x1. Now it's worth noting that these are very different, aren't they? You can see just by looking at the matrices, well, they look different. This is a row, this is a column matrix, this is a 1x3, this is a 3x1. So it's very important, that order. Okay, so it shows that these are very different matrices by the size. Now we have something called a square matrix. Now we deal a lot with square matrices in maths, okay? They're very, very handy. A square matrix is a matrix with equal number of rows and columns. So the same number of rows as it has columns. Okay, that's a square matrix. And we'll see later on in maths that there are special kinds of square matrices. But basically, this one, that's a 2x2 square matrix. Very, very common matrix, that one. We use it a lot. This next one is a 3x3 matrix. So these are both square matrices because they have the same number of rows as they do columns. So 1, 2, 3 rows, 1, 2, 3 columns. Now a diagonal matrix is a special kind of square matrix where all elements are 0 except for the leading diagonal. Okay, so what's the leading diagonal? The leading diagonal, it's easiest to see here, is the diagonal of the matrix that goes from the top left-hand corner down to the bottom right-hand corner. Okay, that's the leading diagonal. That's the important diagonal. Okay, so make sure you understand that leading diagonal. From top left corner to bottom right corner. Okay, it is not the other way. Okay, that other way is not an important diagonal. That is the important diagonal. Okay, so whenever we're looking at things, that leading diagonal is the one that we look at that diagonal. And so a diagonal matrix is where we have numbers on the elements that are on that leading diagonal, but all the other elements are 0. You can see there. Okay. Now you can see that our matrix can hold any types of numbers. Now, with an identity matrix, it gets very important because here we're talking about 0 and 1. Okay, 0 and 1. So a diagonal matrix is where that leading diagonal is all 1, and we call it an identity matrix, okay? And it has a special symbol, I, okay, that capital I. It has to be a capital, yes. So you can see I've got here up to a 5 by 5 of a square matrix, but obviously our square matrices go up all the time. You can have 6 by 6, 7 by 7, 8 by 8, etc., etc. And you can see that that leading diagonal, those elements are all 1 and everything else is 0. Now we have something called a 0 matrix. That's a matrix with 0 as a value of all its elements. Okay, so you can see these are all 0 matrices. Okay, now it doesn't, I won't go into that now. Okay, I was just going to say we don't just write equal to 0. We have to write the matrix out showing all the elements equal to 0. So we can use our matrix to represent network diagrams. Now, a network diagram is a diagram showing connections between things or people. Okay, so here I've got 4 country towns connected by roads, as shown in the network diagram below. Represent this diagram as a matrix with the elements representing the number of roads between the towns. Okay, so let's look at this matrix. Now, let's go through and read this. Here I'm saying town A, town A. Are there any roads from town A to town A? No, there's not. There's none. From town B to town A, there is 1 road. From town C to town A, there is 1 road. From town D to town A, there is 1 road. From town A to town B, there's 1 road. From town B to town B, there's no roads, is there? There's no loopy roads there. From town C to town B, there's 1 road. From town D to town B, there's 2 roads. We can see that there, so that's represented by the 2. Okay, so read through it that way. See if you can understand it. Now this is from the text that we're using. And I just wanted to show how this is showing, more information, different information. The distances in kilometres along 3 major roads between the Tasmanian towns of Launceston, Hobart and Devonport are displayed in the matrix below. Okay, so from Hobart to Hobart, 0 distance. Makes sense, doesn't it? They're the same place. But from Devonport to Hobart, it's 207 kilometres. From Launceston to Hobart, it's 160 kilometres. From Hobart to Devonport, 207. From Devonport to Devonport, 0 kilometres because you're there. From Launceston to Devonport, 75 kilometres. Okay, so from Hobart to Launceston, there's 160 kilometres. From Davenport to Launceston, there's 75. And from Launceston to Launceston, it's 0 kilometres. Okay,